Good day for everyone. St. Petersburg time is 10 o'clock, and let's start international our conference, International Conference of Interactive Collaborative Robotics, ICR 2021. So today we have age presentation, and let's start. The first presentation is a technique to provide an efficient system recovery in the fog and edge environment of robotic system. Offer are Anna Klemenko and Igor Kuляев from Russian Federation. Let's start, please.
Dear colleagues, today I present a paper named A Technique to Provide an Efficient System Recovery in the Fog and Edge Environments of Robotic Systems. Nowadays, the fog and edge robotics have become an efficient mechanism to provide robots with low latency computational data processing services. The low latency data preprocessing is of a high importance for such robotic areas as assistive robots, mobile robots, robot swarms, and many others. The transformation from the cloud robotics to the fog and edge robotics has emerged from the intersection of fog computing and the robotics. It enhances the capabilities of the endpoint robots, improves the system latency, network load, and security. Besides, the intersection of the robotics and multi-access edge computing relates to such concept as the follow me one. Follow me concept considers terms such as follow me cloud, follow me edge cloud, move with me, and others. The key idea of this field is that the migration of the virtual machines or containers or processes are presupposed to the appropriate nodes of the edge fog to follow the endpoint application in the angle of its geographical position. Considering possibly a high frequency of the reconfigurations in the fog and the application downtimes, which accompany the application relocations, the issue of the quality of service provisioning is relative and up to date. The current paper considers the reconfiguration in the fog edge as a computational procedure which emerges spontaneously and brings some extra computational workload on the nodes. Besides, the time of reconfiguration is important in the focus of the quality of service for the robot application. Considering the reconfiguration task as the computational one, which has to choose the new nodes for processes relocation, such task includes the workload distribution task with the input data as some nodes, which must be chosen in the fog. The time of these procedures could be reduced by the workload increase on the other nodes, but such approach decreases the reliability function dramatically and potentially leads to the node's failure rate increase. In this paper, a new technique is presented to improve the reconfiguration efficiency from the reliability angle. It is based on the choice of the appropriate methods of the nodes monitoring and control, which can reduce the system recovery time and so to improve the reliability function of the nodes meeting the quality of service requirements. The edge and fog computing applications in the robotics field are presented in the slide. They are firstly autonomous connected vehicles functioning, predictive maintenance in the robot complexes, supporting of the fog architecture. Besides, a cost-efficient strategy is proposed to implement deep learning at the edge. The robot's learning procedure is implemented by means of the edge computing concept. Consider a reconfiguration as a computational procedure which implements the task's relocation from the faulted nodes to the operational ones. In this paper, we consider the node failure as a particular state when the node cannot participate in the task processing due to any reasons. Failure detection procedure precedes the reconfiguration. The sum of failure detection and of the reconfiguration times determines the time of system recovery. Consider then that some computational tasks are processed on the fault or edge nodes, and there is a predetermined time period in which the computational tasks must be solved to provide the appropriate level of the quality of service. So the reducing of the system recovery time affects the task solving time and consequently the solution quality. Also, if the workload generated by the computational tasks can be distributed through the available time, the possibility of the node's workload decrease emerges, which causes a positive effect on the node's reliability functions. Further, we presuppose that the efficiency of the reconfiguration procedure is determined by the reliability function value in the end of the operation time period. The time of system recovery can be reduced in different ways. By the intensive computations in a shorter time periods, by the parallelization of the computations, and as it is proposed in the current paper, by the usage of combinations of particular methods of the system monitoring and reconfiguration, which allows to improve the efficiency of the system recovery in the angle of the node's reliability function. Indeed, consider the situation when configuration tasks are processed by computational nodes with high workload, while the remainder of the time the nodes work in operational regime. Then the process can be described by the following scheme, which is presented in the slide. Also, reliability function equations are presented too. And the graphs demonstrate the dependency between the reliability functions and the share of reconfiguration time of the nodes. It is seen that in case of the reconfiguration time growth, the reliability function degrades dramatically. And here it is shown how reconfiguration proceeds. The reconfiguration consists of failure detection time, search space forming time, and the scheduled task solving with the usage of the search space formed. The current research is devoted to the failure detection time reducing. So it is proposed to try to reduce it by the choice of the appropriate control and monitoring method. And we can choose from the centralized, decentralized methods and the method with the distributed leader. To estimate the monitoring and control methods, some abstract estimations were developed, and they're presented here in the slide too. You can see the estimates for the centralized control method, for the control method with the distributed leader, and the decentralized method. as well as computational complexity of the failure detection was estimated too. And here one can see the simulation results. In these graphs, a dependency between the failure detection time and the nodes number is shown. It is seen that the centralized method, of course, gives the best result. And by the way, the best result is reachable when the follower fails, while the failure of the leader gives us the worst result. Here one can see the graphs with the dependencies of failure detection times and the network diameter. It is also seen that the best results are for the follower failures and for the failure of the follower in the centralized scheme. And these dependencies are for the failure detection time and the number of failed nodes. It is interesting that in such cases, the best results are for the method of distributed leader because of reducing of the data to be transmitted through the network. And here the illustration of estimations of the computational complexity of the failure detection. Well, some preliminary conclusions were made, and here one can see that, for example, a distributed leader method is preferable when we have a relatively small number of nodes, relatively small network diameter, and high network dynamics with the simultaneous fail of 0.25 nodes and more with the condition of the small network diameter, and the presence of the nodes with the highly static features. From this, the following technique was developed, and one can see that the main feature which can help us to choose the appropriate monitoring and control method is a group with static nodes. If we have them, so we can try to choose the method with the distributed leader. In all other cases, the decentralized control is much more preferable. And the main conclusions. A relation between the time of the functional tasks processing and the total time of the reconfigurations affects the node reliability. The approach with the distributed leader can give brilliant results only if very few reconfigurations are produced by the leader failure. The technique proposed allows to choose the appropriate control method according to the node's functioning conditions. That's all. Thank you. Thanks for your attention.
Okay, thank you a lot. And is any author of this presentation here? Anna Klimenko and Igor Kilaev. Is anybody here? No? Okay, let's start the second presentation. Petr Smirnov and Artem Kovalyov from Russian Federation. The paper is dedicated payload stabilization system in a service robot for catering.
Hello.
Let's start, please.
Hello, can you hear me?
Yeah, we can hear you.
My name is Ekaterina Cherskih, and I will present this article because the author cannot attend today.
Okay, let's start.
So, this research, the design.
Oh, full screen, please.
Sorry. Wait. Okay.
Okay, thank you.
This research, the design of a mobile robotic platform is proposed, which differs from analogs in the ability to stabilize the payload due to a combined solution based on the use of PhD controller and suspension system and payload control. The device will solve common applied problem in the field of robotic service associated with the need to use such robots mainly on flat surfaces. Their purposed solution allows to reduce the cost, simplifies and optimize the work of the robot in the restaurant premises. On this figure, you can see the proposed schematic diagram of a service robot for performing the function of a waiter. The movement of such a device is carried out by 4 engines, rotating omnidirectional wheels, which allows the robot to move in any direction without the need to perform complex maneuvers. And at level 4, this picture, shown a sensing unit, which includes wide-angle cameras, optical sensor, and laser rangefinders, as well as pressure sensor, which are used to implement localization and navigation algorithm in the restaurant premises. The laser rangefinders is offset to the edge of the device's circumference and allowing to determine object around the object, about 270 degrees. There remains blind zones and covered by 6 optical sensors. Wide-angle cameras of this device are necessary for visual localization. Laser rangefinders are used in case it's impossible to determine an obstacle, for example, a chair leg. And pressure sensor in the robot are used for emergency shutdown of engines in a collision if the system could not detect optical or the above described sensor failed. So also included this block, there are component module and batteries. Trays with drink and food are placed in an isolated complement. It's a block 3 to ensure the safety as well as protect the hardware. At level 4 of the device, there are attachments for human-machine interaction. It's touch screen cameras, arrays of microphones. The door that insulated the compartment in block 3 is controlled by 2 magnetic locks and can be unlocked by client when the phone scans the QR code displayed on the screen of the interaction unit. Based on the proposed model of a service robot and a review of existing stabilization solution, a system for monitoring the stability of the platform and its payload was developed. To solve this problem, the following solutions have been implemented. Before introducing a stabilization system for a tray with a payload, it was necessary to perform a comparative analysis of possible solutions to this problem. When comparing the key requirement for them, are determined the ability to work in the limited space of a mobile platform, as well as requirement for a control system. These characteristics are important due to the size limitation of the indoor platform. To meet this requirement, it's proposed to consider the stabilization mechanism. Classic manipulator, any controlled mechanism capable to performing the function of a human hand when interaction with object. Steered platform is a kind of parallel manipulator that uses an octahedral strut arrangement, and gyroscopic platform. This is a device designed to stabilize individual objects or devices. So, based on these results of comparing solution to stabilize the payload, the mechanism of the gyroscopic platform was selected. That mechanism is easily to implement, does not require a large volume occurred in the robot, which meet the criteria of an embedded system. The purposed system consists of eternal measurement models and control and servo drivers that stabilize the nodes. The IMU sensor is an inertial measurement device that allows robot to determine a position in space. This system uses a linear quadratic regulator to stabilize the engines. The proposed system will allow robot to control the tray during movement or emergency braking when an object is appear on its rail. Based on the purposed model, the gyroscopic platform system was tested, and figure 3 shows the operation of the tray, stabilizing control and tracking to the set position in the event of emergency braking. You can see that the maximum deviation from the target position in the case of emergency braking was 0.3045 radian, and the minimum was minus 0.1067 radian at a time interval of 120 seconds. After the disturbance, the system remains in a stable state. By introducing the purposed system into the service robot waiter, it's possible to control the position of the payload during the movement of the robot. The design is similar is engineering to a mechanical gyroscope, allowing you to expand the ability to transport the payload without compromising its integrity. Under the intelligent transportation is assumed between rooms or in the same rooms, which are located in different parallel lanes with a passageway. Also, this design allows you to additionally check in the event of malfunction of a suspension system. And compared to the steerable platform, the resulting design is easy to assemble and sufficient to stabilize flight during transport. That's about all. Thank you for attention.
Thank you very much. And can you answer some questions? Do you know this work?
Yes, I know this work. I can try.
Okay. I have a little question. What platform do you use for simulation? Maybe MATLAB or ROS?
I can suggest it looks like MATLAB, but I'm not sure that I can answer it.
Okay, and how do you simulate the EMU sensor in MATLAB? I think it's not easy task.
I'm sorry, I can answer that question because I am not attend with this.
Okay,
when
and
they simulated.
We have another question in the chat. Is the robot protected from thieves and hooligans?
Yes, as I already said, that there is QR code displayed on the screen of robots, so nobody can steal the food and drinks.
And you have a physical model of this robot, yes? Or no?
I'm afraid that I can't answer these questions.
It's just it's just a model of robot, or you have a physical model. You cannot understand.
I understood, but I personally don't know because I'm only presented.
Okay, thank you very much. So let's start our next presentation. The authors are Eduard Melnik, Irina Safronenkova, and Sergei Kapustin from Russian Federation. The paper is the efficiency improvement of robots group operation by means of workload relocation. Okay, let's start.
Dear colleagues, let me introduce the results of our research paper called The Efficiency Improvement of Robots Group Operation by Means of Workload Relocation. The current paper deals with the problem of workload allocation in a heterogeneous group of UAV during the area monitoring under the changing environmental conditions. In the current research paper, it was shown that it is important to take into account the influence of environmental factors on the UAV movement because of onboard energy resources limitation. On the stage of UAV's distribution by the scan band, it is impossible to take into account changeable environmental conditions. As a result, the entire mission of the mobile group may be unfulfilled. The purpose of the current research is to develop a decision-making technique based on ontological analysis on the need to relocate the workload in a group of mobile robots. The technique allows avoiding the situation when the mission is unfulfilled and decreasing the time of joint mission execution by a group of robots. Currently, monitoring systems are widely used in many areas of human activity, such as industrial production, infrastructure facilities, the socio-economic sphere, in healthcare, in the field of observation of natural phenomena, and prevention of their dangerous consequences. More than that, the high requirements of a great number of monitoring systems application actualizes the problem of effective functioning in difficult conditions. The most promising architecture of control subsystems of complex systems is a distributed architecture based on cloud, edge, and fog computing. This architecture solves common tasks, including control tasks in the cloud layer, while data collection tasks and preprocessing tasks are solved as a rule by means of edge and fog devices. The example you can see in this slide. On the basis of such architecture, some distributed complex systems were implemented, including a multi-robotic complex on the basis of heterogeneous UAVs group as a monitoring system component. Multi-robotic complexes usage allows to decrease some conflicting and difficult to achieve requirements applied to individual multifunctional robots in a group. However, the main lack of a multi-robotic complexes operation is a limited onboard energy resource. To solve this problem, robots retransmitters, which can be used as a group leader and a data store, are introduced into the group. It is important to notice that the environment where a mobile robot performs assigned tasks has a great impact on the amount of consumed onboard resources. In view of the fact that a mobile robot has limited time for the problem solving, it is necessary to take into account environmental factors. Otherwise, a situation may arise when the mobile robot is not able to complete the assigned task. Let's consider the stage of the UAV distribution by scan bands. This task is to determine a specific scan band for each UAV of the subgroup. As can we see from the picture, a sub-area S is divided into n bands with a width no more than L. First, it is necessary to determine input-output UAV points for each band. For each band, it can be determined by 2 points, as can be seen from the slide. The coordinates of input-output points are presented in the following slide. The UAV leader assigned to a given sub-area defines a scan band for each UAV. To avoid emergency situations, it is necessary that UAVs move in the same direction in adjacent sub-areas. The UAV leader makes a decision about input-output points for each UAV subgroup. For example, according to the minimum of the total movements of the UAV assigned to these sub-areas. Each UAV leader puts the obtained values of input-output point coordinates into a distributed ledger to make these values available for the rest of the UAV's leaders. In this paper, we suppose that a UAV group has to scan some area. Moreover, the distributed architecture of a control systems should be implemented on the basis of cloud, fog, and edge computing. Since the environmental conditions in which the UAV group operates are difficult to predict, changeable, and have a direct impact on the amount of consumed onboard resources, then after assigning scan bands for each UAV, a situation may arise when a certain UAV is not able to perform the assigned task because of the limited resources. Multi-robotic interactions involves the collective solution for a common problem. It means that each mobile robot has to act in the best interest of all of the group to successfully complete the mission. If the URV and both resources are insufficient to complete the task assigned to it, the following solutions to this problem are possible. The first one, workload allocation between the URVs included in a group in such a way that the mission assigned to this group is completed on time. The second one, extra resources involved through the devices of the fog layer to perform the assigned task. And the last ones can band redistribution. We will assume that each URV is aware of a resource status and localization in space of its neighbors, which are in the radius of direct communication. Every URV of a subgroup sends its data about resource status and its localization in space to the URV leader. The decision-making technique on the need to relocate the workload in a group of mobile robots is presented in the slide. Thus, each URV is able to assess the state of its resources to solve the subtask allocated to it. If these resources are not sufficient, then the URV, which has information about the neighboring URVs, generates a proposal to the URV leader about a possible choice for workload allocation to the computational resources of the neighboring URV. The URV leader, in turn, makes a decision on the expediency or inexpediency of this relocation. If the URV does not find choices for workload allocation from among its neighbors, then it informs the leader about this, and it makes a decision either to attract extra resources from the fog layer or to redistribute the scan bands. The URV leader makes these decisions on the basis of production rules applied to the ontology model. The procedure of an ontological analysis has shown its effectiveness in workload problem solving in distributed systems of different types and describes in detail in our previous studies. This procedure includes the following steps. Initial data classification according with ontology classes, which describe a specified domain. Application of production rules to ontology classes in order to restrict the set of computational nodes obtained as a result of collecting information about available resources. Making a decision on the preferred set of nodes for workload relocation. To describe a specified domain in the form of ontology model sufficiently and correctly, it is necessary to form a set of concepts which are represented in the ontology as a class hierarchy. Some examples you can see in this slide. Here you can see a class hierarchy and a fragment of developed ontology model in an open source ontology data protege. We will assume the following. Every URV involving in the group has a limited onboard resource and a radius of direct communication. Fog devices are static and have some computing resources. Below we consider two possible cases of workload relocation. The first one is when it is possible to relocate the workload to the nearest URV. The example of a production rule of this case is presented here. The second case is when the workload relocation to the neighboring URV is impossible. Then it is reasonable to relocate the workload to the fog node. The example of such production rule is presented in this slide. In accordance with the decision-making technique on the need to relocate the workload described above, there are two choices for solving the current problem. Workload relocation within the groups, URVs, and engaging resources from the fog layer. In both cases, we mean the use of extra resources. It is also worth noting that in these cases, there are changing environmental conditions, changing distances between the URV leader or between URVs, which have a direct impact on the workload distribution. We assume the main characteristic of the environment is its dynamics, which we mean as the number of workload relocation per unit of time. During the mission, the mobile robot spends on board energy resources to solve a wide range of tasks, including optimization, related to the organization of the group's work. Currently, such problems are solved using various evolutionary algorithms, the solution quality of which increases with the increase in the number of iterations they perform. The dependence we can see in this slide. In this paper, we are considering the following case. We suppose that after URV distribution by scan bands, there is a situation that the available resources are not enough to complete the mission. In this case, it is necessary to redistribute the workload between the URVs of the group or involve the devices of the fog layer and do it as quickly as possible. The purpose of our experiments is to obtain comparative estimates of the amount of computing resources involved in the workload allocation problem solving, using the method based on ontological analysis and the method based on local device groups under the different environmental conditions. The local device group based method is iterative and it was carefully described in our previous studies. In this paper, we studied the monkey algorithm and the annealing method from the point of view of possible extra performance using. Here, we can see the dependence of the amount of involved resources for the ontology-based method and the LDG-based method on the number of workload allocation per unit of time, when the time of workload allocation is equally to 1/1000th of the time of scanning for the monkey algorithm and annealing method. And the results of a similar simulation when the time of workload allocation is equally to 1/100th of the time of scanning for the same algorithms are presented here. Based on the given graphs, the following conclusions can be drawn. With an increase in the number of workload allocations, the volume of engaged resources increases. The effectiveness of using the ontology-based method in a dynamic environment is higher than the local device group method. Ontology-based method allows to decrease the amount of engaged resources up to 44%. The proposed technique makes it possible to increase the time of cooperative mission performance. That's all I wanted to say. Thank you for your attention.
Thank you for presentation. Is any author of this presentation here?
Yes, I'm here. My name is Irina Safronenkova, and I'm one of the authors of this paper. Can you hear me?
Okay, yes, very good. We can hear you. And any questions, please? I have a little question. Do you use some modeling system? What modeling system do you use for modeling the UAVs?
We used a mathematical model of the task of scan band distribution, which was early proposed by Sergei Kapustyan. And we use Excel to simulate some results with which demonstrate engaging extra resources.
Okay, thank you. And you in one slide you show how UAVs create map of environment, and the areas of every UAVs are not intersected with each other.
Yes, it's one of their restriction in this task.
Okay, thank you. Another question, please. I think there is no another question. So thank you a lot.
Thank you.
The next presentation is algorithm for radius review of cyber physical systems operating areas using unmanned aerial vehicles. The authors are Alexander Denisov and Dmitry Levanevsky from Russian Federation. You can start, please.
Thank you very much. Good morning. Just can you see the slides?
Yeah, we see slides. Please, yes, full screen. Yes, okay.
Okay, so let's start. Thank you very much. Good morning, dear colleagues. My name is Dmitry Levonevsky. I'm senior researcher of the St. Petersburg Federal Research Center of the Russian Academy of Sciences. And this paper, Algorithm for Radio Survey of the Cyber-Physical Systems Operating Areas Using Unmanned Aerial Vehicles by Alexander Denisov and me. So, cyber-physical systems that operate in open areas are subject to accidental and deliberate destructive influences from the environment. The deployment of CPS over such large areas can lead to the fact that individual components of the CPS will encounter difficulties in navigation, fail under different influences of the environment, leave the coverage area of wireless networks, and so on. So a number of increased requirements are imposed on the CPS infrastructure. In particular, node connectivity should be secured. Okay, when designing CPS for open areas, it's also necessary to take into account that the environment can have a significant impact on the radio signal propagation and thus hinder the communication of components. This research deals with static obstacles such as trees, small buildings, soil moisture, and uneven terrain that may suppress signals. To enhance the connectivity of nodes, we propose to use radio survey of the territory using UAV. This allows determining the optimal placement of radio elements of the system. Well, of course, there are numerous high-level means of providing node connectivities. For example, overlay networks such as wireless sensor networks, WSN or MANET, mobile ad hoc networks, and other. These networks work in dynamic environments. They are easily reconfigurable. So in case of node loss or environment changes and so on. But these solutions count to the network layer of system interconnection. So consequently, their disadvantages are that they complicate the system architecture. We are required to support routing protocols, and we will face network delays. So to avoid the negative consequences of these solutions, we should use the physical and channel layers of the system as much as possible before implementing the network layer. And for the static environment, we can explore it as follows. We use a UAV, unmanned aerial vehicle, with a radio transceiver, a camera, and a depth sensor. The radio transceiver is responsible for setting the signal level from the gateway throughout the CPS and also determining the signal level from extraneous sources. Camera and depth sensor are used to build a 3D map of the area. We use it also because soil moisture can also affect the propagation of radio signal. And using these sensors and cameras, we build the 3D map of the area. Well, there are known formulas that allow us to compute the attenuation of radio waves when passing through obstacles through the surveyed area. So we can see these formulas here. And here is how we, here is an example how we compute the attenuation coefficient. To ensure the possibility of using inexpensive UAV to survey the territory, it's required to take into account that they possess a low carrying capacity and low volume of batteries. To solve this problem, we propose the following algorithm. The point of this algorithm is to split the surveyed area into parts of the biggest size that can be scanned by a UAV in a unit of time, And then we find the shortest and the fastest way to survey the entire territory. This figure depicts an example how can example of the result of such algorithm application. Here, the UAV moves along in the shape of spiral, scanning the area, and then it returns to the base. For modeling, we chose an area with we modeled and modeled an area with randomly located obstacles such as trees, small buildings, uneven terrains. Radio modules were installed against along the perimeter, and based on the collected data, the following map of signal level changes was built. The figure shows the loss of data transmission in the territory of the CPS operation. As can be seen from the figure, along the edges of the territory under consideration, where the radio modules are located, the loss of the signal is minimal, since there are no obstacles there. But in the center of the study area, there are noticeable signal losses due to the presence of various obstacles like buildings, water, and so on. So the conducted research was aimed at providing sufficient radio signal level to ensure CPS node connectivity. It allows us to build the map of radio signal level and determine the areas where signal is insufficient. So it's possible to consider reconfiguring transmitters in such areas, installing new transmitters, or, if possible, eliminating obstacles. Further research will be aimed at improving the proposed algorithm for automating workflows and data exchange between CPS devices. Additional noise immunity of radio models is also among the key objectives of the study, as well as some another work. So here are the references. That was all. Thank you very much for your attention. Thank you.
Thank you a lot. Any questions, please? You can answer by voice or print your answer to the chat. Well, I have a little answer, at least a little questions for you. What depth sensor do you use on UAVs?
Okay, I'm not sure that I'm able to answer because of the physical part of this research was done by my colleague, Alexander Denisov. So I just lack competency to answer such questions. I'm sorry.
Do you use the simulation in MATLAB? Yes?
Yes, yes, as far as I know.
Okay, so thank you. Another questions?
You're welcome. Thank you.
There is no other questions, so let's start another presentation.
Thank you.
Thank you. The problem statement of cognitive modeling in social robotic systems. The authors are Galina Gorelova, Eduard Melnik, and Irina Safronenkova from Russian Federation. Let's start the presentation. Okay.
Dear colleagues, let me introduce the results of our research paper called The Problem Statement of Cognitive Modeling in Social Robotic Systems. In connection with the rapid development of robotics, the problems of interaction between humans and robots considered as social interaction problems are becoming more and more urgent. At the social level, these problems include identification and exclusion, the possible negative consequences of robots and people interaction. Practical information about such consequences in different areas of robot use may be considered insufficient. In this paper, it is proposed to use an approach to research based on simulation modeling to obtain additional information about the object, which is defined as the social robotic system. The emergence of a new type of robots which are capable to communicate with people interactively at a social level, theoretical searches and practical implementation of the ideas of social robotics have become one of the promising directions in the development of digital humanities. Human-robot interaction is involved in various areas of our lives, such as smart enterprises, smart cities, smart houses, and smart territories. This fact actualizes a whole series of problems of the humanitarian, legal, technical, and others. The purpose of this work is to show the possibility and necessity of applying the apparatus of cognitive modeling to the study of a complex system of interaction between humans and robots, and designated in this case as the social robotic system, as well as to consider possible formulations of tasks in the study of SRS and present the results of their cognitive modeling. To carry out cognitive modeling of interaction in social robotic systems, we will consider several possible tasks formulation. The formal description of a single structure element of a cognitive map and its examples are presented in this slide. The edges between the vertices can display both a positive and a negative relationship between them. Here we can see the examples of positive and negative feedbacks. Here we can see examples of positive and negative cycles. Figures A and C show the examples of a simple positive cycle. All edges in the cycle are positive, or there is an even number of negative edges. In figure B demonstrates the example of a negative cycle. There is an odd number of negative edges in the cycle. In real social robotic systems, there are both single structure elements, for example, at the level of a person and his smart home, and a large number of elements and subsystems interacting with each other under conditions of cooperation or opposition to each other, if we consider competing, conflicting systems. In this case, the model in the form of a cognitive map is mathematically represented by a sign-oriented graph. Now we are going to consider the first task, which includes the statement of the problem of interconnection of partially interconnected robots with a person. Here we can see an illustrative example of a system consisting of 8 vertices, a human, and 7 robots. The cognitive map is developed at the first stage of cognitive modeling. The study of the problem of the properties of the cognitive model is carried out using various operations on the matrix of relations of the graph, which is also shown here. At the second stage of cognitive modeling, the properties of the developed model are analyzed. For example, we can analyze the degrees of vertices. Here, the analysis of the vertex V1 is presented. On the basis of such analysis, we can determine the most significant vertex that has the greatest impact on other vertices. In this case, the vertex V1 human with the highest degree can be considered as the most significant, most of all influencing the other vertices. We can also determine the weakest vertices. Analysis of the cycles of a cognitive map allows to determine negative and positive cycles. In this slide, there are 2 of the 27 cycles of cognitive map selected, 1 negative and 1 more complex positive cycle. This allows judging the structural stability of the system by the ratio of its negative and positive cycles. In this example, the model's structure is stable because it has an odd number of negative cycles. Now we're going to consider the second task. In this case, we consider the interaction of 2 robotic human control systems. In this slide, we can see 2 systems consisted of 1 human and 9 robots. Here we are going to consider a cognitive map path analysis. Using the cognitive modeling complex system, which is an authorial software system, it is easy to analyze all possible paths from any vertices of the graph. In this slide, we can see one of the variants of paths from the vertex V1 human to the vertex V9 human 9. There are 11 such paths, and only one of the negative paths is marked in the figure. Negative path is a path in which there is an odd number of negative edges. It can be interpreted as follows. If human 1 begins to positively act, then this action positively initiates 3 robot, which further positively affects 6 robot, whose actions reduce the effectiveness of 4 robot, and so on. As a result, the considered path is a negative path, weakening the efforts of human 9. Now we're going to conduct a cycles analysis. In the slide, we can see 1 negative and 1 positive cycles, which are highlighted in the figures. In total, there are 67 cycles in the model, of which 37 are negative and 30 are positive. Next, we're going to conduct the analysis of the stability of the model to disturbances. The analysis of resistance to disturbances is carried out according to the result of calculating the roots of the characteristic equation of the matrix of relations of the cognitive map. For stability, it is necessary that the largest in modulus number of the characteristic equation of the matrix of relations be less than 1. Modeling of scenarios of possible development of situations is carried out by means of impulse modeling, the results of which are presented in the slide. In order to simplify a visual analysis of the experimental results, only 7 simulation cycles are presented in the slide. In this case, the vertices are selected based on the results of the analysis of their degrees and half degrees. They are VID V1 human 1, V9 human 2, V7 6 robot, and V14 robot 5. As can be seen from the slide, initiation of actions at the vertex V1 leads to the initiation of the vertex V9 at the second step of the simulation. At the third and fourth steps, V7 and V14 come into play. At the same time, the tendencies in the system develop in an increasing oscillatory mode. The system is not stable to disturbances, and this is consistent with the previous analysis of the roots of the characteristic equation. The methodology of cognitive modeling of complex systems and the corresponding tools proposed for research in the subject area of social robotics can contribute to a deep understanding and disclosure of problems in this area. Imitation cognitive modeling helps to justify various management decisions, anticipating the possible development of processes in complex systems and preventing undesirable consequences scenarios. The 2 simple tasks considered in this paper and the corresponding cognitive modeling of the social robotic system represent the main idea and possibilities of studying such systems. The transition from a model to real problems may require a significant increase in the number of system elements and relations between them, as well as the use of not only cognitive maps for simulation modeling, but also more complex models such as functional graphs. That's all I wanted to say. Thank you for your attention.
Okay, thank you very much. Is offer here, as I know.
I'm here, Irina Safronenkova here, and I try to answer your questions.
Okay, maybe some questions from another participants? No? Okay, a little questions. Why some cycles are negative and another are positive? What's the difference between different cycles?
Just a second. The cycle is positive when it has an odd number of negative. Just a second. The main author of this presentation is Garina Gorelova, and we use her authorial software program. So I have some difficulties to answer such question, but I'll try to do it. Just a second. The cycle is positive when all ages in the cycle are positive, or there is an even number of negative ages. And the cycle is negative when there is an odd number of negative ages in the cycle.
And what does it mean? What mean negative edges, positive edges?
Edges show the connection between the vertices. They can be positive or negative.
Okay, and what it means? That edge is positive or edge is negative?
Edge is positive when one vertex act as just a second, has an the edge is negative when we have a negative feedback, when the system is amplifies the action of one vertex to another vertex.
Okay. Okay, thank you, Elodge. Another questions, please. I think there is no another questions. So thank you. And the next presentation is semantic segmentation in the task of long-term visualization. The author are Lukasz Buresz and Ludek Müller from Czech Republic. Let's start, please.
Hello, my name is Lukasz Buresz and I am going to present you the paper with name Semantic Segmentation in the Task of Long-Term Visual Localization. For the introduction, I would like to say that the ability to effectively represent the local visual information is the key to a vast range of computer vision applications. The range of these applications may contain image alignment. Basically, at the core of the problem, there is a challenge of extracting the local representation of a location of the key points. The key points are typically distributed sparsely in the image and in an invariant manner to various image transformation. The problem of the long-term visual localization can be described as follows. Estimating the 6 degree of freedom camera pose from which a given image was taken is seen as a representation. Visual localization is a key technology for augmented, mixed, and virtual reality. Even in robotics and self-driving cars can be used. Long-term visual localization has multiple subtasks in the pipeline where the improvements to the state-of-the-art can be made. A few open areas where the improvements can be achieved. The first step in the pipeline is usually the detecting of key points end-to-end trained neural networks. The next part is key point descriptors, which is used later for matching purposes. So the third area of improvements can be made in the key point matcher. Originally, key point matchers like brute force or nearest neighbors. We can say that the precision of the estimated location is the most critical parameters, which for the experiment the ARC and day-night dataset was used. It is a subset of the original ARC-N dataset, which contains 1.5 million 3D points and 369 query images. This ARC-N day-night dataset consists of 4,328 reference images and 922 query images. In the sum, there are 824 images captured in the daytime and 98 images taken in the nighttime. As a benchmark, we used one of the benchmarks which can be found on the webpage visuallocalization.net, and it has been used in many state-of-the-art conferences, workshops, and so on as a standardized way how to compare the performance of the visual localization code and so on. In the visual localization, actually, it is based on the Schur's proportional ranking method. The evaluation service defines a set of thresholds. In our experiments, we used, at first, it was a superpoint. The superpoint is self-supervised framework for training interest point detectors and descriptors suitable for multiple view geometry problems in computer vision. It is based on a fully convolution model that operates on the full-size images and jointly computes pixel-level interest point locations and associated descriptors in one forward pass. The next component is supergroup. It is a neural network that matches two sets of local features by jointly finding correspondences and rejecting non-matchable points. Assignments are estimated by solving a differentiable optimal transform problem whose costs are predicted by a graph neural network. For semantic segmentation, we use hierarchical multi-scale attention for semantic segmentation. The main goal of semantic segmentation is to label all pixels within an image. Most of the previously mentioned methods were combined in hierarchical localization pipeline. In our experiments, we were focusing on two main parts. The first part is tuning the hierarchical localization parameters to achieve better performance on the mentioned dataset, which is RHEM. I'm going to briefly mention the parameters. For the day images, we set the netclat to retrieve the 50 most similar images. We used a grayscale preprocessing resize the images to be 1600 pixel wide. We set superpoint to retrieve up to maximum 2048 key points with 0.01 threshold. We set the non-maximum suppression radius to be 3 pixels, and we used a supergroup pretrain odor weight and used 100 single iterations. And the rest of the parameters were unchanged. For the night images, we did the same, only with one difference, which was that we didn't perform the resizing. And the first results are shown in the table, which mean that our previously mentioned parameter configuration outperforms the original result. In our second experiment, we used the semantic segmentation, and we pre-segmented all of the query images, and we labeled the images with all of the classes which were provided, and we grouped all of the classes into the 4 groups of the classes. We named the classes human, vehicle, nature, and sky. For example, in the nature you can find, for example, trees, grass, and everything what is related to the nature. We used this semantic information for thresholding the image based on the selected group of the classes, and then use this thresholded image for to be actually input to the wool pipeline. And the results are shown in the table, and we perform all of the combinations, and the human group of classes perform the best. We did this experiments only on day query images, because on the night query images the semantic segmentation methods doesn't perform well. In the conclusion, we can say that removing the dynamic object can be beneficial to the localization accuracy, and removing the humans and vehicle groups of the classes help the most accuracy manner. The semantic segmentation may be a good way for filtering unwanted information. Okay, and that's all, and thank you for your attention.
Thank you very much. Is any offer is here? I think not. Okay, so let's start the next presentation. development of multi-sensor emotional response system for social robots. Esther Hafter, Charlotte Perry, Nicholas Corio, Harry Person, and Xueo Zhu and Chungsu Li from United Kingdom. Please start presentation.
Loneliness is an important public health issue, but at times like this, with pandemic safety measures employed by governments across the globe, old age loneliness has been a primary concern. With care homes locked down, no visitation, many elderly experiences loneliness. With or without the pandemic, loneliness is a huge issue in our society today. While it's not a direct cause, loneliness has been shown to have correlation with malnutrition, sleep problems, and depression. There have been many kinds of social support intervention developed, but these may not always be available or desirable. One example is animal-assisted therapy, which is a well-used method, but it can bring a lot of negatives as well. Infections, phobias, allergies, or other animal-caused injuries are the four main issues surrounding this method. Artificial agents can present an innovative alternative to these issues. Studies show that social intervention robots can help reduce the feeling of loneliness either through direct interaction or by initiating conversation between the users themselves, which is highly encouraged at times when visitation in care homes are banned. Many social robots on the market only use one emotion categorization system at a time. Let it be facial emotion recognition or sound analysis, not many machines combine multiple recognition systems and they limit themselves at basic emotions. MERS, aka Multi-Sensor Emotional Response System, offers an innovative solution to allow our artificial social agents to give more empathetic responses and to think on a complex level of the user's emotional state.
Our computer vision system identifies the emotions it detects in a few steps. First, it uses a high-speed, real-time facial detection algorithm called a HAR cascade to detect the face looking at the camera. It then uses a neural network to identify the expression on the user's face. This system works in real time and is modular. While it comes pre-trained with a robust dataset, the emotions identified can be changed by an end user by simply providing a new labeled dataset. The algorithm automatically detects the emotion types from the names of the training data folders, and training and testing data that are used are lightweight 48 by 48 pixel grayscale PNG images. The software comes with a script that transforms images from either a CSV or image format into one that matches the one that the algorithm uses, the 48 by 48 pixel images. At base, the algorithm detects a plethora of emotions. With neutral expressions as its base, it also detects joy, anger, sadness, surprise, disgust, and fear.
Here we have one of our colleagues, Nick, testing out the facial emotion recognition software, making sure that it is all completely trained.
The fur touch sensor for this project is made from 3 different materials: the pre-made fur, the conductive fabric, and conductive thread. Several prototypes were made from these for the project, and finally setting on the denser style design. This was proven to show the most reliable results, giving similar results each time it was tested. We did initial testing using a picoscope. We used this to determine, using the chosen touch types, if they could be differentiated between. This also showed us which touch types worked and what sort of input we expected to receive into the lily pad. The different touch types we chose were single directional stroke, multi-directional stroke, scratch, poke, and pat. We used these results to then start gathering data for training the neural network. For each touch type, we gathered 400 samples over a 2-minute period. We then tested the trained neural network using the different touch types on the fur to check that the results were as we expected.
Here we're testing the system with simulated inputs. We simulated both the expression input as well as the touch input, and the output can be seen. Our system is built using sensor fusion technology to combine the data taken from both the visual and tactile sensors. This means that the robot can build a more solid comprehension of exactly what emotion the user is feeling. After this data is combined, the system computes and then outputs a suitable response. This response is designed based off of emotion theory, meaning that the responses it is designed to give have been scientifically shown to aid in empathizing with humans. It will help to calm an angry user or soothe a sad user, for example. Through the combination of visual and tactile data and the emotional response output, we have created a system that we hope can interact very well with not only our target audience, but also with anyone who might benefit from the advantage of having a social robot to interact with. We hope that our system will be able to support those who, particularly in the current climate, are unable to socially interact with others. Our system represents a new turning point for social robots. Combining the cutting-edge tactile fur technology with facial emotion recognition means that this robot is capable of understanding human emotions on a deeper level to what we have seen before. In the past, social robots have had limited technology to understand their users' emotions and feelings, but now we hope that our system will allow social robotics to take that extra step further.
Very interesting presentation. And is any author of this presentation here? I think not. Oh, so let's start the final presentation. Igor Polintsev, Evgeny Shandarov, and Vladimir Zhelonkin from Russian Federation. The Meow, a social robot platform for school.
Hello.
Okay, let's start with full screen presentation.
Just a second. Can you see my screen?
Yeah, very good. You can start.
Hello, dear colleagues. I'm Igor. I'm presenting our article, Meow, a social robot platform for school. Let's start with a small preface to my speech. Using social robot as a teacher is proposed for a long time. The concept was firstly proposed in 1984 by Pater, and since then many works have been done in this direction. Latest results and publications show that using a robot could be beneficial for the learning process, and especially if a robot is effective in such fields as learning foreign language, learning new words, speech therapy for inclusive learning, and etc. Also, investigations show that the physical embodiment, physical presence of robot on lessons is more effective than using a virtual counterparts, which means that robot could be beneficial for the studying process. Our collective from Tsuruba University has some experience in these directions. We have implemented, we are doing social robotics since 2012. We used to create a social robot for school based on Now platform. It's an humanoid robot commonly used for social robotics. And during this work, we developed quite big system for school applications. This robot could be used in high school as a teaching tool for programming on informatics and technology. When the students, when they program not only not laptops and personal computers, but real machine, the robot. Robot could be used for primary school where robot is a source of information, an organizer, and personal tutor for the kids on such subjects as math, literature, outward work, and etc. And also it could be useful for teachers and management staff because robot can, for example, check in students which come to the class in the morning if we implement face detection system. Anyway, robot is useful because it can provide individual work with each child and can pay attention to each student every day, and it decreases the it just helps the teacher because teachers are really short of time. Okay, this is some photos of our project. It's now robot and kids now robot, sorry, and kids with it. Using the now has some limitations because now have a quite high cost. We cannot sell it to schools of Russian Federation because each now costs around more than 1 million of rubles. That's why we decided to create our own robot, which had some basic requirements. It should be cheap, it should be attractive and friendly for kids, and it should be very simple. It should have minimum degrees of freedom, it should be stationary, and so on. That's why we developed a robot cat. Everyone likes cats, especially kids, because in Russia many families has cats as pets. Robot is based on Raspberry Pi controller. It has touchscreen display with 3.5 inches diagonal. Robot is equipped with a camera, USB microphone, power amplifier, and speaker for pronouncing sounds, proceeding voices, speech, and so on. Also, it has movable paws and tail, lids in ears and mustache, and built-in power source. Body. Okay, we had a lot of versions of Meow. The first one was made of plywood. I have it with me here. Other versions of Meow were made on 3D printer from PLA plastic. This is a very good technique for producing the prototypes. And current Meow is blue colored and have dimensions 14, 17, and 18 centimeters. It's just like a key. Robot software. Robot is independent device. It does not require the internet connection for the work. All interaction with user is carried out via screen and voice. We use browser as a main source where the information is shown. Browser represents the menus, the faces, and so on. That's why we use browser, VDD technologies, Ajax, JavaScript, cloud databases, local network communication, database, and here means the local robot database, and many programming languages. So the IP of robot consists of 4 main modules: the vision module, voice synthesizer, speech processing model and control model. Voice synthesis was carried out with the help of Google Speech IP for the first time for first prototype. Now we transited to the Rush voice free pocket with Russian voice Anna. In the future, we plan to train our own unique voice for Meow, but I think it would be a little bit later when we will start to sell this robot to the Russian schools and kindergartens. Speech processing model was for the first time implemented using Yandex IP. It is a very good tool for speech processing, but it requires fast internet connection to Yandex servers, and also you should pay for using that. And that's why, while demonstrating robot, we do not often have the internet connection. That's why we decided to develop the onboard speech processing unit. For it, we used Pocket Phoenix library and Russian language acoustic model. This works on board, but there are a lot of limitations connected with the vocabulary size, the speed work, and accuracy, and so on. Raspberry Pi is not so powerful processing unit. That's why there are lots of limitations for speech detection, but we are working on it. Sorry. Vision model was developed for recognizing some patterns. We have cards with traffic signs, for road sign detection we used the OpenCV library and I think the classic algorithm for sign detection. I will not stay on it because it's not so interesting. And the control model is realized through Robot apps. Robot app is piece of Python application which implement machine to human interaction scenario. It should be developed by the teacher because it contains all educational and methodological structure, all phrases, reactions, and so on. That's why it would be better if teachers would develop it rather than programists, as we are. The script is running in operating system of Meow. It calls, it detects all video signs, detects speech, processes speech, generates voice, and so on. Calls for emotions. Currently, we developed 4 emotional states: sad, happy, and smirking, so on. Emotion is shown on the face of robot. You can see it on the picture here. Also, if, for example, Rebecca gives a correct answer to the question of robot, the happy face appears on the screen, the ears are turned green, and paws go up, tail starts moving, and so on. And some other cases for non-correct or wrong answers, and so on. We developed several robot apps which we already tested on now. It is road sign studying. It shows a robot card with a sign, and the robot detects it and tells the kid what sign it is, some little poem about it, and in this way robot study the signs with kids. English word studying, there are two modes of this robot app. In one mode, kids studying some English words. Robot gives short Russian poem which ends with English word, and kid should remember this word and Then in second part of the robot app, when robot tells him this point, he should remember this word and tell it to robot. In riddles, it's just for demonstration mode. Robot asks gives some riddle, and the user should return the answer already. Multiplication table robot just basically asks what is the result of multiplication of 6 on 7. Again orally. And testing systems, it's an application running on laptop where the question with multiple choice answers are presented. It selects the answer, and if this answer is correct, a robot says gives some positive emotional response, and if wrong, negative response. Also, the robot doubles the information given on screen orally, just vocalizes it. So the developed robot platform is not final version, it's not perfect. There is a lot of things that should be done. The average speed of onboard speech synthesis is about 22 milliseconds. It's a very good result because we can give very fast answers to kids, to users' questions, and so on. Currently we have rather low accuracy of speech processing because we're using onboard speech processing, around 75%. And we have non-optimal road sign recognition algorithm, which is which consumes a lot of computing resources. That's why the speed time for recognition is rather high, about 1.4 seconds. But if we use more powerful controller with bigger operating, with bigger ROM, then we will have better time for recognition. Okay, we presented this robot on Robocup in Russia, or on Robocup Russia Open in Tomsk, and in the past weekend in Technosreda Festival in Moscow. There were a lot of kids on these exhibitions. Kids had positive reaction to robot, said that it's cute and nice, and even this robot attracted much more attention than now because everybody loves cats, as we claimed before, probably because of this. That is all I would like to tell you. If you have any questions, please.
Thank you for your presentation. Any questions from participants? Please, questions. So I have some questions.
Yeah.
What controller do you use in your robot?
Raspberry Pi 4.
Raspberry Pi 4, yes. And what operation system do you use on Raspberry Pi?
Sorry, can you repeat, please?
What operation system do you use on
Linux Raspbian OS, as far as I remember.
Linux Raspbian?
Yeah.
Okay. And before this robot, as I understood, you used Now robot.
Yeah.
And I have a little experience in programming Now robot, and I can say that it's very difficult to programming the Now. And what programming language do you use for develop programs for Now robot?
For now, Now was equipped with Now Key framework, which implements all resources for speech processing, for video processing, and so on. We, based on this Nauki framework, and also added some Python, PHP, Bash scripts to make a connection with a personal computer, because now does not have a screen on it, and the communication with now could be handled only orally or kinesthetically, which is not enough for using now in educational process. For control system and etc., we developed our own web apps which launch this control.
Okay, thank you. And what about robotics operation system? Do you use it? Do you plan to use it or not?
Sorry, robotics operating system, it's a special OS for Raspberry or what?
Yes, it have a version of robot operation system for Raspberry. Do you plan to use it or not?
I have heard about this just from you, but I don't understand what advantages it has over classical Linux system, because we use OpenCV and so on. We can just put any library and package on classic OS, and I will study what are the
because a lot of algorithms for speech, for computer vision, there is a lot of such algorithms in robot operation system.
You mean the special programs which are optimized for Raspberry Pi?
Yes.
Okay. Thank you for your advice. I will try.
Okay.
Thank you.
Another questions, please.
Have you studied the experience of using
Yes,
Tamagotchi?
have you studied the experience of using Tamagotchi? Your device has few resources. What task can it solve effectively?
Okay, studying with Tamagotchi, it's quite interesting idea. I have not studied it yet, but I will, because there could be some interesting aspects in it. Probably we can use it in our future work. And about few resources, yeah, you are quite right, because Raspberry is very short of resources. All processings are done very slowly, and they should be optimized for Raspberry Pi. We use short vocabulary, about 50 words in our apps, and each app has its own vocabulary, again, for optimization. So, for example, if you launch the riddles robot app, the special vocabulary for the riddles with about 50 words is loaded to the operating system, and speech module can detect only these 50 words, and again with quite low accuracy. So limitations are quite high, but we can detect video, proceed speech, and so on. It is not so perfect as it would be on personal computer, but for Raspberry for now it's just not so bad, but it could be better.
Okay, thank you. As I see, there is no another questions. So thanks for all participants, for organizers, our
Thank you, Roman, for being chair. I think our session is over. The ICR conference is over as well. Thank you all for your participation, for interesting reports and questions. So goodbye.